Okay, so in this video I'll be talking about the Hilbert space. So basically in my previous videos I talked about metrics and what they are and how we're going to be using them in a general sense throughout the rest of this playlist. So this video we'll be talking about Hilbert spaces. All this really requires is familiarity with linear algebra and the previous video. So that's what makes this a good video to talk about now. So basically for a real Hilbert space, what exactly is that? So basically a Hilbert space is really a vector space that has an inner product, has an inner product. And so basically, let's just start with the standard, vector space definitions. Let U and V be members of H, where H is a vector space, and U and V, for every U and V is a real number, because right now we're dealing with the real Hilbert space. And of course, the vector space has to be closed under addition, and also closed under scalar multiplication. So U plus V is equal to some W, and that's also a member of the vector space. So again, closed under addition and closed under scalar multiplication. And keep in mind, this scalar can be any real number. That's an important property. And of course, let's not forget the zero vector has to also be included in H. Now, for the Hilbert space, essentially you have that the inner product x and y is equal to y or x, and essentially. An example of the inner product really is the dot product works very well as an example, because really a dot product is an example of an inner product. So if we have some kind of I just want to do it up here. If we have some vector like x1 xn, and then we want to take the dot product with another vector x2 xn. Essentially, these are just two arbitrary vectors with n components. Now, of course, if we want to find the dot product, all we really do, we just do the transpose. Actually, I'm just going to call this y. I'm going to call this y and then call this yn, just to make the notation easier to deal with. So that's y1. So, anyways, so the dot product would be equal to the transpose of x times y. That essentially that is the dot product, which essentially is a good example of the inner product. And essentially, any vector space that has an inner product defined on it is a Hilbert space. And so that's what it is for the real numbers. Now I want to come back to this particular axiom in a minute. So let's go into the complex Hilbert space. Now for a complex Hilbert space, let's just say U and V are members of G, where G is a vector space defined over the complex field. So we have for every U and V's, are complex numbers. That's standard. That's what you expect, and it's closed under addition and also closed under scalar multiplication. And of course, the zero vector is in G. And so basically, but another important part of a complex Hilbert space is that if you do the inner product, it also has to be equal to the inner product of x and y is equal to the complex conjugate of the inner product of y over x. So let's say we have something like, let's say we have like another vector. So this time we have like, x1 xn, and then we want to again stick with the dot product because it's a very it's a really good example, yn. And so essentially we do the same thing. So x transpose y would be our dot product. However, this also has to be equal to, remember the complex, it has to be equal to the complex conjugate of this. So essentially, we have to do y conjugate of this. So I'll just say star for the conjugate. It's equal to y, and then this will be equal to x transpose. And that's essentially what the complex Hilbert space is saying. But notice for the real Hilbert space, there is no complex. It's not complex, so there's no imaginary terms. So really, the complex conjugate of any real number is just itself, because the imaginary term is just 0i. So really, the real numbers can simply be thought of as the complex number is just with plus 0i, plus or minus 0i. Essentially, and so that's pretty much what Hilbert spaces are talking about. And so in other videos, I'll be talking more about the inner product, because here I just gave an example of an inner product. That product is an example of an inner product. And it's interesting to see how exactly the similarities and differences between a real Hilbert space and a complex Hilbert space. A lot of these spaces, I'll be talking about the elements of those spaces are going to be real numbers, but there'll definitely be some spaces that I talk about which will be complex numbers. So it's good to kind of get some kind of understanding of what's going on with the real numbers and the complex numbers, especially with vector spaces, because topology definitely and vector spaces, those really go hand in hand. And so this is pretty much a good stopping point. So I hope you guys enjoy, and I'll see you guys in the next video.